to be able to know the 5-number summary quickly and easily. As always, least to greatest. Laura, 1,000 points right there. And let's do this.
I found him. What's he doing? I don't know.
The 5-number summary is the following values.
He's talking to someone.
From least to greatest, min, Q1, median, Q3, and the max. Nice answers. If you put the 5-number summary in the chat, you get 1,000 points. Keep these answers coming.
What is it? What happened?
Should be, there we go, audio. Chapter 12 makes no sense. No! Chapter 12 is all about probability. Good morning, Hannah. Good to see you there. I didn't have the microphone on. I was like, something's not going to work. I was like, wait a minute. I was like, where's the microphone? And then I was like, I don't have it on, so can't hear me if there's no microphone. Well, Cameron, let's take a look at some Chapter 12. Remember, start early, and you're doing it right there. Great to see you, Abigail and Hannah right there. I really want to make it so I can hear the music myself. It keeps me chill. But good to see everyone there. What problem should we do? Should we do Chapter 12 homework? I love Chapter 12. Should we do the quiz or the homework? Right now I'm doing the quiz. We could just go through and start doing the quiz question by question. It is tough. It is a very mathy chapter. And so great job starting early. Yeah, I know, right? If you get Chapter 12, it's one of those chapters that we can't trick you on. So you have to think about how the rules apply. Remember, there's 5 rules. Probabilities are contained between 0 and 1. The sample space of all probabilities adds up to 1. Complement rule, 1 minus the probability is the probability of the complement. Addition rule, things have to be disjoint atoms. Struggling with high blood pressure on the quiz. Yeah, that's a good tricky one. Let's go open it up right here. Go to the quiz. And let's go find it. We might be able to do most of the quiz. That I could do. How many are on here? Probably can't do all of them. I'd have to go too quickly and not explain what I'm doing. I don't want that. Okay, let's go find the high blood pressure one. There's 24 questions. I found the high blood pressure one quickly. And let me open up Word, and we'll start with the high blood pressure question. And so let me edit this video. The M&M one. Ooh, the M&M one's really good. I like that one. This is with M&Ms. 313. So Chapter 12 quiz, high blood pressure. Got to a 1. Okay, let's go do it. Good morning. Good to see you there, Jennifer. Here we go. Okay, so with this right here, we get a, my gosh, contingency table. The contingency table over here is showing us people who have high blood pressure, people who have cholesterol that is high, and we have the percentages in there. So the probability that a man has both conditions. So what is the probability they are high and they're high? So with this right here, I'm trying to remember how this one goes, if there's any tricks to it. So with this, we are just looking at what's the probability of both of them happening at the same time. So let's go ahead and take a look right here. The probability that a man has both conditions. So its blood pressure is high and also cholesterol is high. And what we should get right here is it should be 100%. Let me open up the calculator. Let's check it right here. Good to see you there, William. So we'll pull open the calculator and we'll double check. Everything should add up to 100%. And it does, of course. So it should be, unless I'm wrong, unless I'm misthinking this problem, it should be that. The probability that a man has high blood pressure is going to be this. So now they're using the addition rule right here. So with the addition rule, we can add together the probability of high blood pressure. So high blood pressure would be these right here. Might need to actually just take a screenshot of this and show you. But think about this. The probability of high blood pressure is going to be one of the two groups. So what should we do to these numbers? So the probability of high blood pressure, look, I have the highlighter clicked right there. I do. Where I do. So high blood pressure, we should add them right there and get 31%. I feel like there's a trick I'm not remembering. the probability that a man with high blood pressure has high cholesterol. So the probability of a man with high blood pressure has high cholesterol. Now this is where we need to look within and go here to, given someone has high blood pressure, what is the probability of high cholesterol? So what is going to be the mathematics? Think of it this way right here. Can anyone tell me the mathematics right here for this one? The probability of somebody, great job, Aaron, right there. We got through some points. The probability of someone with high blood pressure having high cholesterol. I've got blanks for you to fill in right there. So it helps when you draw it out to be like, okay, of the people with high blood pressure, what's the probability they have high cholesterol? You added them, but you got it wrong for part 2. Oh, let's see. Hopefully I'm not doing this wrong here. Hopefully I've not made some errors. We'll take a look to see if I'm making an error or so. Is this what you did right here? Is that what you did right here? Is that the mathematics you did? I think is that what you did, Hannah? That should be right, unless I'm misthinking it. So should be that right there. Is that what you got right there? And then wants to 3 decimals, so 452.452. Oh, for part 2, the next one. Okay, let's see here. Oh, so it's saying that one's wrong? The probability that a man has high blood pressure is this. I'm going to double check. What's the probability that he has high blood pressure? The blood pressure is, unless I'm looking at it wrong, you do yeah, I love the M&M one. That's one of my favorites. I feel like there is something to this one that I'm forgetting. The probability that a man has high blood pressure, if it is known that he has high cholesterol, is this. So now they're changing it to the other way. What's the probability of someone having high blood pressure if it's known they have high cholesterol? Wondering about that part too. So now they're doing it the other way. And they're going within here. So if it's known he has high cholesterol, what's the probability he has high blood pressure? So we're looking at this right here. And it's just the other way of doing it. Given they have high cholesterol, what is the probability? And I hate to start out with missing one, but I feel like, is anyone seeing an error? Because people are saying, yeah, I think so, right? That should be right, Sarah. I think so. Sounds right to me. So unless we're misthinking this. So that's going to be, I wonder if they want like a 0 on it or something. If they wanted a 0, that's ridiculous. It says to 3 decimals for all these, right? So the probability that a man has high blood pressure, second answer is going to say 1. No, we got it. Okay. I was like, what are we, I did this one the other day, and that's how, yeah, exactly. That's what I thought. Because I was like, I feel like there's a trick or something that I'm missing. But that's all the answers right there, and that's how to do it. Once again, the first one just starts out with one of the probabilities. Then the next one is just adding the probabilities, and then we're doing the mathematics we showed right here. Can you explain D again? So this is the way D looks right here. The probability, it can be read the probability of somebody who has high cholesterol having high blood pressure. So here's the mathematics here. You would add together those 2 probabilities up there that I've circled, and then the top probability is the one right there. Does that make sense, Abigail? So that's the ones, and the circled ones are the ones below. So it's out of that total right there. So it's doing a marginal, or excuse me, a conditional distribution. So hopefully seeing the math right there kind of helps out. Yeah, and so let me know if there's an error or something on yours. I've seen my person actually say you got it wrong and you got it right. I've seen it one time, I think, where it said the answer was 0, and then I think my person made an error. So I've actually seen my person make errors. It's super rare. In 10 plus years of teaching, I've seen like one time where I'm like, my Pearson made an error, like their computer program didn't do it right. That's a really good one. It's pretty good. I mean, I like it. The M&M one is one of my favorites. It's a tough one though. The M&M one is a super tough one. It's very long also. It's a good one too, right? A lot of this chapter is my favorite. Here we go, the M&M one. Ooh, good to see you here, Michael. So the M&M one, let's do it. This one, if you can do it, you can do a lot of this chapter. So Stat Tool 1, Chapter 12 quiz. So with this one right here, you're going to use all the rules of probability. M&Ms. You're welcome, Hannah. So the first thing you want to do is you want to take all of this and write down the associated probabilities. So you want to take this table right here and go to a piece of paper and write down the probabilities. So notice if I write right here, purple, yellow candies. Okay, so if I write, what's that going to equal? What's that going to equal? Start out with the very first thing. And I've made errors writing these down before, so that's where I get a problem wrong, is when I put the information wrong. So please correct me if you're like, no, Brian, that should be this percent. 20%, yep. So the reason I often have you work it with me is because usually when I miss a question, it's because I write something down wrong and I just read the problem wrong. If you read the problem wrong, you just go on the wrong track. I still know how to do it. I just make an error reading a problem. That's the most common miss. Sometimes I get things wrong because I just make an error in how to do it. I've done it. So next I'm going to write down probability of red. And the probability of red is 20% also. And orange, oh, those ones right there. So now probability of blue, probability of orange, and probability of green equals to 10% each. And then brown make up the rest. So how are we going to figure out the probability of brown? So think about what you could do with these probabilities right here to figure out the probability of brown. How would you figure out the probability of brown if we have, and we'll put brown as BR. So it's going to be 30% because you can add these up. Because the sample space of all probabilities has to equal to 100%. So if you add these up, you should get 100%. So brown has to be 30%, which is going to go barely off the screen. Exactly 1 minus 0.70. So that's the sample space of all the probabilities. Notice how we haven't even really read what their problem states yet, because we're interested in just writing down what we know to start out. This is going to help us with this problem in solving it, and it's going to make it a good bit easier. What is the probability that an M&M is blue? Well, that's about as easy as it gets. It's 10% because it literally says that. Next one right here. What is the probability that an M&M is orange? My gosh, they're just going for the easy ones. So red, another 20%, and all these right here. Orange is also 10%. Please tell me if I type. Oh, red. Ooh. Now be careful right here. Brian already started to make an error. If we say red or orange, we got to throw Cameron 1,000 points for that right there. I didn't notice it last second. What rule are we using when we say red or orange? So you should know the words. We talked about the words in class. When I say red or orange, we're using what rule? The addition rule. So what is the condition that we have to pass for the addition rule to be used? Red or orange is the addition rule. And what condition do we have to pass? To add things together, they must be what? No worries, Cameron. I think you corrected me, right? Disjoint or mutually exclusive, which means if we get a red M&M, it can't also be orange at the same time. Does that make sense? So a red M&M can't also be orange. Is that a fact of the world? Like if I get a red M&M, it can't also be orange. That's what disjoint means. If one thing happens, the other thing can't happen. So if I pick a red M&M, I can't also get an orange, like it can't also be orange. That same M&M, the one I pick, can't also be orange. So that is definitely disjoint, and we just add together red or orange. And what's the probability of red or orange? Red or orange. So red right there, or orange. The probability is what? Because we're using the addition rule. Red or orange. 30%, add them together. You got it. So that's the addition rule. Good stuff right there. I was like, why are they just doing the same concept of what's a probability? Nope, they're doing the addition rule. What is the probability of not yellow? So what rule is this? If we say not yellow, what rule is not yellow? Like what concept are we using when we do not yellow? Because the probability of yellow is 20%. The complement, exactly, complementary. So if yellow is 20%, what is the probability of not yellow? So if yellow is 20%, what's the probability of not yellow? So it's either yellow or not yellow. Abigail got it right there. Great job, Abigail. It's going to be 80%. And next we see, did you see any spotteds? They're just being weird. just being weird. I'll be weird. See if it'll accept that. Okay, so now we're going to draw 3 M&Ms, and this is where we start to get to the multiplication rule. Suppose you pick 3 M&Ms in a row. So you're going to go to the bag, and you're going to pick an M&M, pick an M&M, pick an M&M. This is where we start to get into the multiplication rule, and let's see how we do it. The probability of getting 3 blue M&Ms. So explain to me in a sentence what happened. You went to the bag, and your first M&M was blue. Your second M was blue. M&M was blue. Everyone's already got some answers. So what words are you using? And let's say this is a really big bag of M&Ms. Good to see you here, Emma. Hey, Emma. Big former student, right? I think there are 1,000 points for Emma showing up. I think. Maybe I'm just seeing students here from this semester who I'm like, and the and rule. So if you're hearing and, so we would say I picked a blue M&M and a blue M&M and another blue M&M. And here's the thing. We are assuming that each blue M&M we pick is what of the previous blue M&M. So what are we assuming when we do the multiplication rule? These are the things you should know, and we practice. We say every time we use the multiplication rule, we know that what we picked previously is what of what we're picking, independent, which is different than disjoint, mutually exclusive. Those are different rules for different concepts. They do overlap in some ideas, but they don't mean the same thing. They can kind of imply each other, but we'll get into the details on that at another time if you want. So the answer is blue, and then blue, and then blue is going to be 0.10 to the third power, which is that right there. If you don't believe me, 0.10 times 2, 3. There we go. Got it right there. Don't times by 2, 3. 0.10 times 0.10 times 0.10. Next one is the probability of the third one being the first brown. So if you picked 3 M&Ms, and this is where it gets a little complicated, and the third one was the third brown, your first M&M would have been what? If the third one was the first brown, your first M&M would have been what? Your first M&M would have, if the third one was the first brown, this is the first brown, right there on the third one. The first M&M would have been what? Any other color. It would have been not brown. So we have here not brown and not brown. Your first M&M was not brown, and your second M was not brown, and your third M&M was brown. So who knows the mathematics right here? If you see what we wrote out, you see the first M&M was not brown and the second M&M was not brown. Notice how I'm saying and when I multiply, and the third M&M was brown. Does that make more sense, Cameron, right here? Like the first M&M I picked was not brown, and the second M&M I picked was not brown, and the third M&M I picked was brown. So there it is right there, 0.7 times 0.7 times 0.3, which is going to be, oh my gosh, I can almost do it. I think it's 0.147. Am I right? Probably not. Let's try it. Hey, 0.147. Still got it. Maybe. I can do it. Got this. Okay. The probability that none are red is this. Okay. So we're looking at none of your M&Ms are red. So the first M&M would be what? If none of them are red, the first M&M would have been what? If none of them are red, then the first M&M would have been what? If none of your M&Ms are red, the first M&M would be what? None of them are red. Anything but red. So it would have been not red, and the second M&M would have been not red, and the third M&M would have been not red. So what's the probability of the first not being red, and the second not being red, and the third not being red? Trying to work it out, 0.24, 0.48, 0.504. I think it's that, but how did I get that? How did I get that? The first was not red, and the second was not red, and the third was not red. You have to use the complement to get the probability of not red. So the first was not red, and the second was not red, and the third was not red. How do we get that probability? So the first M&M was not red, and the second M&M was not red, and the third M&M was not red. How do we get that probability right there? What's the math? I've written out the sentence, and I can say the sentence. The first was not red, and the second was not red, and the third was not red. So what's the math? 0.8 times 0.8 times 0.8, or 0.8 to the third power. A not red M&M and a not red M&M and a not red M&M. 0.8 is obtained by 1 minus 0.2, because the probability of red is 0.2, so the probability of not red is 0.8. 0.8 times 0.8 times 0.8. Oh no, I got it wrong. Well, good thing we got so make sure to solve it with the calculator. Add points, viewers, what? There we go. Use calculators, use your head to check it, use calculators to double check it. The probability of at least one yellow M&M. So this is where it gets tough, and these are my favorite problems. We did a few of these in class right here last class. At least one yellow M&M. This is where people really get stuck on these, especially on the test. So what I want you to do if you see an at least one problem is start by writing a sentence. Write the following sentence for any at least one problem. If you get to an at least one problem, nice job, Michael, right there. I want you to write the following sentence. And the following sentence would be 1 equals at least 1 plus none. Okay. So I want you to think about this. Is it a fact right now in office hours that either at least one of you will get an A or none of you will get an A in the class? What do you think? Is that a fact of the world that at least one person right here right now will get an A for the class or none of you will get an A? Is it a fact that at least one of you will get an A or none of you will get an A? That's a fact. And think about this. Well, because either it's going to be the case that at least one of you gets an A, like one or more, or none get an A. So does that make sense? At least one gets an A or none gets an A. This is now the sample space of everything that can occur because we've listed everything. It's either that one or more people get an A or no one gets an A. The same thing goes for yellow M&Ms. When I pick out my 3 M&Ms, what are the 2 things that'll happen? It's either the case that what? Think of the yellow M&Ms right here. Tell me, and this is why it adds to 1, because one of those things must occur. It's the sample space of everything that could occur, and they're complements. So either this occurs or that occurs. Tell me about the yellow M&Ms when I pick 3. It'll either be the case that what? This is the one we want to solve for. We want to solve for at least one. So it'll either be the case that what? What we want to know. It'll either be the case that what? Either you pull at least one yellow M&M or you get no yellow M&M. Does that make sense? You're either going to get at least one yellow M&M or no yellow M&M. So here's the thing. We want to find this one, so why don't we just take in mathematics none over to the other side? So we're just going to take in algebra, mathematics, this over here, which means we have to subtract it. And now we have the probability of at least 1 is 1 minus none. What do you think we have to solve for now? Because we can get at least 1, which is what we want to know. What do you think we have to solve for now to get the answer? And there are other ways of solving this that are less fun. What do you think we have to solve for now? And I'll show you the longer solve, which you might do on the test to double check. What do you think we can solve for now? Solve for the probability of none. So tell me this. If you were to pick M&Ms and none were yellow, what's the probability of the first is not yellow and the second is not yellow and the third is not yellow? What's the probability that the first is not yellow and the second is not yellow and the third is not yellow? You know what's funny? Unless we made an error on another one, I think I know the answer to this question. Unless I watched me make an error. Yeah, there we go. 0.8, 0.8, 0.8. And I knew the answer because that was the probability of not red, because red and yellow had the same probability. So the first is not yellow, and the second is not yellow, and the third is not yellow. So with that right there, that is the probability of none. So 1 minus 0.8 to the third power is the probability of at least 1. And so what I did right there is I remembered, as you were answering the question, that we already figured out that for the previous question, red and yellow had the same probability, and then I just subtracted that by 1, or I did 1 minus it. Does that make sense what I did right there? So I was like, oh, we just already found that, so let me just subtract 1 minus that, and the answer is this. Notice how they add to 1. but that was with red, but red had the same probability of yellow. So we were able to figure out the probability of no reds, and the probability of no yellows is identical for 3. Now, that is the way to solve it. We'll probably do some other at least one problems, hence I want to go to the next one. I have been enlightened. The not fun way of solving this is to do the following, is to go through here. Oh, no. This is the not fun way. Gosh, really? Really? Okay, well, there's yellow. I'm going crazy. Okay. This is all the ways you could get at least one yellow M&M. Does that make sense? I know the sum of these probabilities equals 0.488. I hope so too, Cameron. You'd have to go through here and find 0.8. Oops. So this is the not fun way. Point. What do you think we'd have to do to all these probabilities then? I forgot a 0 on that, I think. Oh, 10. Oh, I think, wait. Yeah, no, that shouldn't have a 0. Yeah, that's why I was like, that looks wrong, because that should be bigger than the other one. Oh my gosh. What should I have to do to all these probabilities? Which this is not the way to do this. Like, we didn't even teach you this way of solving it. So you'd have to take all these probabilities and add them up. You'd have to add together all those probabilities because it could be the case that you get one yellow M&M as your third M&M, or the second one, or the first one, or you got 2 yellows this way, or this way, or you got 3. Notice how between all of these, what word am I saying to add them up? What word was I saying to add them up right here? Yep, exactly, because all of these are the ways you could get at least one. So you could get it this way, or 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 this way. And if we check the mathematics, it should add up to 0.488. And that is the addition rule right there with the multiplication rule, because you're saying the first was not yellow, and the second was not yellow, and the third was, and the first was not yellow, and the second was yellow, and the third was not yellow. So I did all the ways with the multiplication rule to figure out the probabilities, then added up all the ways with the addition rules because they're disjoint, and then I found the probability that way. That's the longer way, and you have to kind of know a little bit more about how to get the permutations. There's other ways too, but I think the easiest way is using the sentence structure. That's the easiest way. And we never do at least 2. People have asked, like, what about if it says at least 2? That won't be on the test. Next question, let's do it. I really like the M&M problem. I think it goes over most of the chapter, to where if you can do the M&M problem, you can probably do most of this chapter. So I think the M&M problem is like the, can I do the M&M problem? Would I be able to do different versions of it if we changed it up? You can probably do most of this chapter if you can do the M&M problem. There is like law of large numbers and stuff too, though. What else do we have? Surely another question. To use the addition rule, do the probabilities have to add up to 1? They don't have to. Because think about this. That's only when they're complements. Because what about if I ask you, the sample space must add up to 1. But what if I say, what's the probability of a red or a yellow M&M? You can't get a red and yellow M&M at the same time, or with the mathy stuff. So what's the probability of a red or a yellow M&M? The rule is that they have to be disjoint / mutually exclusive, which means they can't occur at the same time. Like you can't get a red, yellow M&M, so you can't have them both occur. So can we do the one year period? Yeah, the car one. That's a really good classic one. So the probability of a red or yellow M&M would be 40% because we just add them up. And they have to be disjoint mutually exclusive. That is the rule. Make sure when doing the addition rule, things are disjoint mutually exclusive. Exactly. And I say them together because they mean the same thing. There's 2 consumer car ones. I really like those ones. That's an easy one. The playlist one is like, and that one's easy too. Maybe we did that one last. Where's the car one? I don't like that one. That one's quick when you know to solve for it. We're almost there. Car one. Car one. Here we go. All right, let's do both car ones. And okay, so with this one right here, the first thing you want to do for any probability question is write down the what's. So the first thing you want to do for any probability question is write down the what's. Remember this for the test. It's going to help you out, and I'll start doing it right here. What do you want to do right when you start any probability question? Write down the what's. For any probability question, start by writing down the what's. The probabilities, you got it, William, right there. Now notice, your car is either going to get repaired 1 time, 2 times, or 3 or more times in a year. So your cars are either going to get repaired 1 time, 2 times, or 3 or more times. What is another thing that could occur that's not listed here in the sample space of everything that could occur? Because your car is either going to get repaired 1 time, 2 times, or 3 or more times. What else is there that could occur that's not listed? Because maybe your car gets no repairs, right? So how would we figure this out? Because think we have 1, 2, 3 or more. So what's up, Colin? Good to see you there. I appreciate that. So it's such positivity. We love that. Extra credit in the chat. So how would we then figure out the probability of 0? Because 0 is the only thing missing from the sample space. The sample space is everything that could occur. So how do we then figure out 0? The probability of 0 is what? Well, let's add together these probabilities. Because it could be this, or it could be this. Oh my gosh, I'm over here. Exactly, subtract from 1. Great job, Abigail, right there. Good practice. And that's the complement of those things. So if it doesn't have this, or doesn't have this, or doesn't have this, probability of 0 is this. And now we have a sample space. So take a look at this. What do we have as the probability of no repairs? We already found it, right? The probability of no repairs is this. What's the probability of no more than 1 repair? That'd be getting what or what repairs? No more than what repair? No more than 1 repair is you got either this or this. Like if I say my car didn't get more than 1 repair this year. I'm not saying it got 1 repair. It didn't get more than 1 repair this year. 0 or 1. And then the probability of some repairs would be what? So I'm showing with the highlighters what the answers are. You add those together. Because you said or, right, Cameron? Because you can't get 0 repairs and get 1 repairs. You'd get 0 or 1, and they're disjoint because they can't occur at the same time. It's not the case that you can get 0 repairs and get 1 repairs in a year, because that year you'd have gotten 1 repair then. So what's the probability of some repairs? What's the probability of some repairs? How would we do some repairs? Like, what's the probability of some repairs? There's quick ways to do it. Because you could just do this. Some repairs is going to be that. Or you could just do that for some repairs, like 1 minus 0.77. So the probability of some repairs is not getting no repairs, so complement of no repairs. Does that make sense? This is the easier version. I think the other one's not too bad either. Like when you see it, you'll be like, oh, really? Really? That's it? So that should do it right there. 0.77, 3, 0.77, 0.93, and 0.23. I think those were the answers. Check, we got it. Now we get to the harder version of it. Yes, oh, of course, we got tons of time. We still got 25 minutes. Let's do the harder version, right? So now you have 2 cars. There is a theoretical problem with this problem, that if you had a car that needed repairs, it would probably be the case that your other car would need more repairs. So when you look at this right here, we get the same sort of information. But we're just asking, does the car need repairs or not need repairs? So what would you immediately do to figure out the probability of the car needing some sort of repair? How could we figure out, using the information listed above, the probability of the car, because it says the probability your car needs 1 repair is 19%, the probability the car needs 2 repairs is 7%, the probability the car needs 3 or more repairs is 4%. So what's the probability the car needs some repairs? We're just going to call this the car needs repairs. So think about this. It's like you could have 19% of the time you need 1 repair, 7% of the time you need 2 repairs, 4% of the time you need 3 or more repairs. So it's listed everything, 1, 2, 3 or more. What's the probability of just getting repairs? Because you could have 1 repair, or you could have 2 repairs, or you could have 3 or more repairs. And they're disjoint because you can't get 1 repair and 2 repairs in the same year. Because if you got 2 repairs, then you got 2, you didn't get 1. You do the bowling? Yeah, bowling one's fun one. So how do we figure out the probability of getting 1 or 2 or 3 or more repairs? And that might be the answer. It looks to be. Great job, because you've added them together. Great job, Cameron. So we just added them. When I say or, we're adding. So the probability of repairs is 30%. And so what is the probability of no repair? If the probability of repairs is 30%, great job, Michael, there. If the probability of repairs is 30%, what's the probability of no repairs? 70%. Great job, Cameron. So the probability of no repairs is 70%. And that's the complement rule, where you just subtract. So either your car gets repairs or doesn't get repairs. Now remember, we have 2 cars. So with our 2 cars right here, what is the probability that the first car did not need repairs and the second car did not need repairs? What's the probability the first car did not need repairs and the second car did not need repairs? Our first didn't get repairs and the second didn't get repairs. Didn't get repaired? What is that? The first did not need repairs and the second did not need repairs. So listen to the key word. The first one did not need repairs and the second one did not need repairs. No, not times 2 though. And here's the thing, Cameron, we're going to throw you 1,000 points. And I want you to see this though. If you do that on the test, notice that immediately the probability you get is what? And I want to point this out here, so I'm going to show it in the notes. I want you to know this error, because if you've done that, what is the answer you just got? And then what alarm starts going off where you're like, uh-oh, like, what would you think? So if that happens on the test, why would you be like, wait a minute? So if that happens on the test, why would you be like, wait a minute, I've done something wrong? A lot of people do that. That's why I'm pointing it out and give you some big points. It's above 1. So it'd be more than 1. So probabilities are contained between 0 and 1. So when we say that the first needs repairs and the second needs repairs, what rule are we doing? The first needs repairs and the second needs repairs. The first needed repairs and the second needed repairs. The first needed repairs. Oh, wait a minute. Cameron. My gosh, Cameron, 5,000 points. Cameron, do you want to say it in the chat or do you want me to say it? Yeah, I know, right? My gosh, my eyes are that bad that, yeah, I know. I thought you did a multiply right there, and you did it perfectly. So 5,000 points. So I was like, I looked, I was like, wait, they got it right. I think I just went between alternate universes where you got it wrong, and then I went into the real universe where you got it right. I was just going between dimensions. I don't think the portal's behind me here, but I was also confused. I was like, wait a minute, it's right. So it's 0.7 to the second power, 0.7 times 0.7. The next one right here, the probability that both will need repairs. So think about this. What is the probability the first needs repairs and the second needs repairs? What's the probability the first needs repairs and the second needs repairs? Sorry about that. Big points for me getting it wrong. You got points because I thought you were wrong, then you got more points because I was wrong, like even more wrong. The first needs repairs and the second needs repairs. The first needs repairs and the second needs repairs. We're using the and word, saying and. First needs repairs and second needs repairs. What is the probability of that? A win-win. We love getting things wrong here. Oh, so I'm saying no repairs is 0.70. The first one was 0.49. The second one should be 0.09 because it's repair and repair. Does that make sense? Both needs repairs is, and that NR stands for no repairs. So it's repairs and repairs, and I've got it color coded right over there. So repair and repair. Does that make sense? 0.09, 0.3 times 0.3 is 0.09, I believe. So 0.3 times 0.3. The first one was this right here. And you know what's interesting? 0.09, yep, sorry about that. So I was thinking 30% probability. At least one car will need repairs. So what they've done right here is they've actually given you a lot of things. Because if you think of everything that could occur, we just found out that both cars, no repairs, both cars, no repairs is going to be, I'll use blue. Both cars, no repairs is 49%. Both cars, repairs is 9%. One of the cars needing repairs, think about this, we've listed a sample space here. What is the probability that one of the cars will need repairs? 5,000 points if anyone figures this out. Use the sample space right here. And we're talking like either which way it could occur. What's the probability that one car will need repairs? Which is not what it asks. It's not what it asks. What's the probability one car will need repairs? Want to have ideas on that? So I think I've listed everything that could occur, so use the same logic. Either both cars need repairs, either both cars do not need repairs, or your first car needed repairs. And you can just figure it out that way. That's a 49 right there. Sorry, it looks, my 9s and stuff are really bad. That's a 49, so it should be minus 0.43. That's a 9 right there. I used the wrong color. Does that make sense to you? I think you're doing it right. I just have colors that are hard to see, or zeros that are hard to see. So it should be 0.47. But here's the thing. With that said, which probability are you figuring out right now? Which one, Cameron, right there? Or did I do this right? Let me think. No, it should be 42%, I think. What have I done? What have I done? For the, let me double check my math. Should be 42%, and 7 times 7 is 49. That's that first one. It's 9%. Oh my gosh. Oh my god. I keep thinking that's a 3 or something. There we go. There we go. So does that make sense? I just can't math today. Because these numbers down here should add up to what? If this is everything that can occur, these numbers down here should add up to what? We're reviewing the rule number 2 that the sample space of everything must add up to 1, because either it's the case that your cars both don't need repairs, both need repairs, or it's the case that one of them needs repairs, and that could be 0.7 times 3 times either way, 0.7 times 0.3, and then there's 2 ways it can occur, so a lot of math can be done here, and this shows the full problem. But here's the thing. At least one car needing repairs, what is the other thing that could occur to finish this problem? It could be the case that at least one car needs repairs, or what? It could be the case that at least one of your cars needs repairs, or what? It could be the case that at least one of your cars needs repairs, or none of them need repairs. So then we can use the same trick. 1 minus none equals at least 1. So at least one car needing repairs. Well, both could need repairs, but the thing is at least one car needs repairs, then it could be both need repairs, but that's contained in at least one. So when we do the sample space of everything that could occur, does that make sense? We say it's either this or this, and that's disjoint, because it's either the case that at least one of your cars need repairs or none of your cars need repairs. So now we can solve out the probability of no cars needing repairs. So no repairs 70%. So it's going to be 1 minus both cars not needing repairs, which is 0.7 to the second power. And when you solve this out right here, you will get 0.51, and that should be the answer to that one. Really good question. Do people feel like they understand these problems better? These are excellent, excellent problems, and that is the complement of the first one right there. But these are some of my favorite problems. Bowling question next. Bowling question next. How are people doing? It's a good one. I love this chapter. It's a tough one, but it's all math. Where is the bowling one? Tell me if you see it like the number. Bowling. We did those during class. What about getting out of class? Yeah, missing the train. That's a good one too. Certain bowler. Here we go with the bowler question. Then we'll do the train question next. So 4 to 6, 50. Set to a 1. Out to 12. Bowling. A certain bowler. Okay. So with this one right here, we need to first look at the probabilities and write down something. Who knows from watching me do these what Brian's going to write down to start this question? Take a moment and see if you know from watching us solve these questions what I'm going to write down to solve this question. See if you can follow the logic, and this is the practice you need to be like, okay, I should start writing down the information I have and figuring out how to use it. What would we write down first? What's the first thing we'd write down right here? So think about the steps we've been doing for other problems. This is where you get good at solving them, and you're like, okay, so I've been watching Brian do the steps. Boom, wow, William, 5,000 points. Even with the follow-up question of let's find the complement, exactly right there. So probability of strike, great job, Cameron, too. Probability of strike, probability of not strike. So William already did the probability of the thing we're interested in. And then William also took the probability of the complement of it, which is not strike right here. That's got it. That's the information we have to start. Great job, William. Even I was going to ask the follow-up. Now what do we write down next? But that's what we have, and we've translated it to our knowledge. What is the probability that they get 3 consecutive frames without a strike? So they would get not a strike and not a strike and not a strike. They would get not a strike and not a strike and not a strike. So what is it going to be to get not a strike and not a strike and not a strike? You do have to assume that these are independent, and it'd be 0.35 times 0.35 times 0.35, not a strike and not a strike and not a strike. So you'd have to assume that they're independent, which are they, or are they on like a cold streak? Ooh. And Cameron, did I do it right there? Okay, good, yeah, awesome. So might say enter all decimals, some of them say that. Nearest thousandths, that's going to be tenths, hundredths, thousandths, so we're going to round that to 3 right there, and we're good to go. What's the probability of them making her first strike in the 3rd frame? So what would happen if they got their first strike in the 3rd frame? Tell me, like, they went bowling, 1st frame, 2nd frame, 3rd frame. What would be the probability, or how would that sound? Like, tell me, watch it happen. Like, watch them go bowling, and they're going to make not a strike, not a strike, strike. There you go. So let's write that down right there, and we're already doing the math. Great job. Are these problems a little bit easier now? I think when you write them down like this, and you write down the notation, not a strike, strike, and then you say the words like not a strike, not a strike, and strike, it makes more sense, and you're like, I'm multiplying because I'm saying and, which is the multiplication rule back here. So just knowing which rules you're using and when is important, And we do have to assume that each of these bowling attempts are independent of previous ones. Are they? Kind of. But we have to assume that to do it. Great job about, oh, does it round exactly to that? I think it does. Wow, that's nice. I gotta hear my sound effects again. Gotta get that fixed. Okay, rounds up, rounds up, rounds up. And we'll enter in the 0. The probability of having at least one strike in the first 3 frames. At least one strike. So this is another at least one problem. So we're going to write our sentence here. So remember, we start by, if you practice the at least one problems with us here. Owen Wilson, wow. Wow. It should be right there, right? Wow. I'll do a few of those during class day, remind me. 1 equals at least 1. Oh my gosh. At least 1. Plus none. Okay. So we're trying to figure out the probability of at least one strike. So we need to figure out the probability of what? We want to figure out the probability of at least one strike. So does anyone already see it? Check out class where I go through this very slowly. We need to figure out the probability of none strikes in the first 3 frames. And we already kind of did that. So here's the thing. We already know the answer to probability of not a strike, not a strike, not a strike. And this is where I sometimes think people like, you have to see we already have the answer to this. It was the first thing we solved for. So we can just go to our answers right here, grab this, and do what? What from what? So just take that answer right there for the probability of none, because we already know the probability of no strikes in the first 3 frames. And then just do what? Take that probability right there, which is the probability of no strikes in the first 3 frames. And boom, you've already done everything. Subtract from 1, and there it is. So those two will be complements because either you get no strikes or you get at least 1 strike, and you have that right there. A perfect game is 12 strikes in a row. So very quickly, the probability of this is strike and strike and strike and strike and strike and strike. And we got to add some new levels in, probably class today. Do we have any levels beyond that? I think we might, William. We have a 400,000 point level. We'll need to add those in. So how do you, nice job, Cameron, right there. Probability of strike and strike and strike and strike and strike and strike. Sounds like I'm going on there. Dun and dun and dun and dun. What's the probability of that? 12 strikes in a row. You get a strike and 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 a strike. 0.65 to the 12th power. And it's going to be very unlikely because every time you multiply probabilities together, they get smaller. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And go to your phone and say, what is 0.65 to the 12th power?
It's approximately 0.005688.
Now, you can't do that on the test, but use things like your phone to double check this, because if you're doing it that way or put it into Google, just make sure you do it right. Round to the nearest thousandths. So this is going to round up right there, and we should be right. We're good to go. So really good stuff right there. Another great question doing the multiplication rule and knowing that each bowl would be independent of previous bowls. The next one we're doing is the late to train question, or catching the train. One of my favorite questions too. I can't tell, I love this chapter. It's such a fun chapter. The chapter 10 questions, as I said, I watched the office hours. I literally gave away, or didn't give away, literally didn't. Good sense, right? I looked at test questions and then came up with my own from them, which it's pretty much like being in class where I come up with questions that are very similar to what's on the test. So you should feel better about chapter 10, I hope, because the questions are going to be kind of like I phrased them in office hours. I mean, I was looking at the test, so. And I came up with my own versions. A student figures that he has a 45% chance. Oh, I got to mark this so people will be able to check it out later. We'll be like, where's the question? We got this. Stat tool 1. I have time for one more after this. So a student figures. Okay. A student figures that they have a 45% chance of being late out of class. If he's late out of class, he has a 20% chance he'll miss the train. What is the probability that he gets out of class late and misses the train? So think about this. You can do it very quickly. He gets out of class late and misses the train. And, ooh, someone already saw the key word right here. So you're saying, what's the probability he gets out of class late and misses the train? So here's what actually could occur. he gets out of class on time would occur 45% of the time, or 55% of the time. And then he can't miss the train, but then there's probability of late, missed train. We'll put just train or sad face because he misses the train. And that's going to be I think it's going to be equal to 0.09. And then probability of late out of class and he catches the train is going to be equal to, I am correct on this. Yep, great job. 0.36. How do you think I got that last probability? How do you think I got that last probability? If he gets out of class on time, he doesn't miss the train, apparently. That's the way the problem goes. So, and then we multiplied the probabilities. I've got it highlighted with and in the middle. So you now know the probability. If he gets out of class late, his probability of missing the train is this. So getting out of class late does change the probability technically, because the probability of missing the train if he gets out of class on time is what? What is the probability? This is a weird question to ask with this one, but if he gets out of class on time, what is the probability he misses the train? It doesn't say it in the problem, but it's implied. That is correct. Yeah, great job, Cameron, right there. I got 3 another 1,000 points. You were right, Cameron. And it is dependent technically, but they've given you the probabilities. Because if he gets out of class on time, the probability of missing the train is 0. It doesn't say that in the problem. I wish it did. But if he gets out of class on time, he doesn't miss the train. So he will always, if he gets out of class on time, which is 55% of the time, he will always make the train. It doesn't say that, it's implied, but good to see you here, Boo. So it is dependent probabilities, but then it gives you the new probability. Like if I say, if it's below 32 degrees, the probability of snow in Knoxville is 10%. But if I say, what's the probability of it snowing and being below 32 degrees, it might not imply that. But if it's below 32 degrees, which happens 40% of the time in January, the probability of snow is 10%. You could then do that. Can we do the at least one light bulb? We'll finish with that. We got a longer version of it during class. I think we have just enough time. I was going to go grab a Monster Energy drink. I'm addicted. I got problems. Let's do the at least one light bulb. We'll end with that. It's one of my favorite ones. And so with this, let's go over here and do at least one light bulb to finish off. And I'm going to go grab a Monster. I should stop. Say that. And I don't. Light bulb problem. 5-pack of light bulb, 2%. What's the probability at least one of your lights is defective? So, get my own. How in the world did I do that? How in the world? Yay, of course, Vicky, yeah. Oh, of course, Vicky's awesome. Everyone knows Vicky. Vicky's the best. I'll tell Cameron, I'll sit here and tell her Cameron says hi. Vicky's going on vacation here soon. But let's see, how in the world did we do that problem? Now, what do you do whenever you see an at least one problem? Whenever you get your at least one problem, this is, if you're practicing this right now, you are going to write your what? If you see an at least one problem, you're going to write your sentence, right? So let's do it. You purchase a 5-pack of light bulbs, 2% of them are defective. So we're going to write here the probability of defective is 2%. Woo! The probability of working is 98%. So it's either going to be the case, and we're looking for at least one is defective. So probability of 1, because one of these things must occur. It's either the case that at least one are defective or what? At least one is defective or what? At least one is defective or what? At least one is defective or what? The probability is or none are defective. So to find this, we need to then figure out the probability of 1 minus none defective. And so what is the probability of none defective? So that means the first light bulb is not defective, and the second light bulb is not defective, and the third light bulb is not defective, and the fourth light bulb is not defective, and the fifth light bulb is not defective. So what is the probability of the first is not defective, and the second is not defective, and the third is not defective, and the fourth is not defective? What is the probability of that? There it is. Because you're just timesing them together. That's got it. Abigail, does that make sense? I know we did it really quickly. We did longer solves of these in class, I think at the start of last class. If anyone can't find, there it is right there. But writing the sentence is the key to these at least one problems. And the more of them you do, you just get to the point where you can like look at them and you can see one of them and be like, okay, I know what I got to solve for now. Like when I look at this problem here, here's what goes through my head. Okay, for a winning sales promotion, 22% are winners, so 78% are losers. You buy 6 of them, what's the probability you win something? So you either win something or you win nothing. So 1 minus win nothing is what we're looking for to win something. So 0.22 times 2, 3, 4, 5, 6. We're not timing it by that, we're doing that. And the probability of winning someone, no way, no way. You win something. Oh, winning is this. So it's 2, 3, 4, 5, 6. I reversed the probabilities. I was like, I've never seen it that high. There we go. See, we can make errors pretty quickly. With that, great job. I'm gonna go grab a drink and energy drink, and I'll be back. Bye for now, everyone. Bye. Bye.